All right. I want to start today with our last spectroscopy topic, which is going to be nuclear magnetic resonance. It's going to take several weeks for us to go through all the different variations of NMR, and so we'll start today with with sort of the theory of how it works and a little bit about the information that we can get from it. So in terms of basically NMR spectroscopy, what we have is the ability to get information about the carbons and the hydrogens that really make up the carbon-hydrogen skeleton of an organic molecule. You can do NMR on other nuclei. You can do nitrogen, which is done sometimes in biochemistry for proteins. You can do metals, but we're going to focus on proton and carbon, and we're going to start with protons. So if you think about having a nucleus, and a proton is a hydrogen nucleus. So if you have this nucleus, it basically kind of looks like the Earth in terms of it has an axis and it's spinning. And first of all, whenever you have a moving charge or a spinning charge, that has a magnetic field. And so we can do things to this nucleus by applying a magnetic field. And it kind of looks like a spinning top is basically how this nucleus looks like. So if we have a gyroscope, which we'll have here hopefully in a minute. If you've ever seen a gyroscope, the inside part of the gyroscope is spinning, and its axis then is kind of wobbling. And the nucleus looks kind of the same way in terms of the inside part of the nucleus spinning, and then its axis will what we will call precess around, in this case, gravity. So when you have a gyroscope and it's precessing or a top that's spinning, it's spinning around the force of gravity. Our nuclei are going to do that, but they're going to be, the force that they're working against is the magnetic field. So when we have a collection of nuclei and they're not inside of a magnetic field, Eli, there's notes over there if you'd like to follow along. When you have a collection of nuclei just not inside of a magnetic field, they're oriented in all 360 degrees of orientation. But as soon as you put this inside of a magnetic field, the nuclei, since they're spinning and since they have a small magnetic field themselves, they have two possibilities. They'll either be oriented with the field or against the field. It's kind of like having two different magnets. You know, magnets have a north and a south pole. And one of these magnets would be our applied field, and the other one would be the nucleus's field. You can have two orientations. They can either be aligned north to south or aligned in the same direction. And one of those two combinations is going to cause the magnets to fly apart, and the other one is going to cause them to stick. So what we have is we have a ground state and an excited state that's formed, but it's only formed when the nuclei go into the magnetic field. Okay, so if I had a collection of protons, like in a sample of water, they're going to be oriented in all different directions. But as soon as I put them inside of a magnetic field, they're either going to be aligned with or against the field. Okay? Now, what we're going to actually look at is we're going to look at the magnetic fields of the individual hydrogen atoms. Nuclear magnetic resonance is a small version of what's called magnetic resonance imaging, or MRI. If you've ever had an MRI or ever seen an MRI instrument, what they do is they stick you inside of the magnet. And what they end up doing is imaging the density of water in your system. An MRI is built to image soft tissue. Well, in our bodies, what's soft tissue made of? mostly water. And so if they can image the concentration of protons, they can get a picture of whatever they're looking at on the MRI. But in this case, what we're going to do is look at the individual fields of the protons, not necessarily their concentrations. So once we have these nuclei then either aligned with or against the field, it sets up two energy states. The ground state is when the nucleus is aligned with the applied field, and then the excited state is when it's aligned against. And sometimes these are called alpha and beta states. But the key thing is we now have spectroscopy. We've got a ground state, we've got an excited state, and we've got an energy gap between the two. It turns out that the energy gap between the alpha and beta states corresponds to photons in the radio frequency range. And so in order to go from ground state to excited state, the nuclei are going to have to absorb so many megahertz of photons. So we're talking about just regular radio frequency here. And when that happens, what will occur is what's called a spin flip. Okay. So that's just basically the same table. Now, just like that picture of the gyroscope, as the nucleus spins, the axis of the nucleus does what's called precession. It has a precessional frequency. It wobbles at so many cycles per second. And that's what's called the Larmor frequency. And it turns out that the Larmor frequency is proportional to the applied field. So if I put the sample inside of a stronger magnet, the nuclei will precess faster. If they go inside of a weaker magnetic field, they'll precess relatively slowly. So that's something that we'll have to keep in mind, is that the Larmor frequency is proportional to applied magnetic field. And there's some constants in there, the gyromagnetic ratio and pi, but that you don't have to worry about that. The idea is that when we use a stronger field, the nuclei are going to precess faster. It's the precessional frequency then that we have to apply. So these nuclei precess at so many megahertz, so many millions of cycles per second. Well, when I apply radio frequency that exactly matches that precessional frequency, the nucleus absorbs the energy and it flips. In other words, it goes from being aligned with the field to being aligned against the field, but it still is precessing. So it's like it's precessing with the field, it gets hit with the radio frequency, and now it flips and it's now against the field. That's what's called a spin flip, and that's how we get from ground state to excited state in NMR. So we put these nuclei inside of a magnetic field. We apply radio frequency. If the radio frequency matches that Larmor frequency or has an energy that fits the energy gap, we flip the spin, and we end up then with an absorption, just like we saw basically with infrared. Now, one of the differences in NMR spectra is that the NMR spectra are going to be very thin. The lines are very sharp. One of the things about radio frequency is that you can control it very well. You can detect it, but you can also take a frequency and you can apply, to 1/10 of a hertz in terms of the frequency. Think about your radio stations. You're going the difference between 99.9 and 99.7 in terms of megahertz. Radios do that, and they're not even all that sophisticated. So radio frequency we can control. We can apply a very narrow band of it. We can also then discriminate very narrow bands. So our peaks are going to be very, very sharp in NMR spectroscopy. Don't worry about what the x-axis is. We'll get to that, what that is, probably next week. Okay, but we see an absorption peak. Now, in terms of instrumentation, NMR probably came about in the 50s, is when it first really became a somewhat commercial technique. The people that developed what we now call Fourier transform NMR, Ernst and Anderson won the Nobel Prize within the last 10 years for that. But instruments have come a long way, and I need to just explain a little bit about how that's happened, because one of the ways I'm going to explain shielding and deshielding is by using the older technique that we used to use. So this is one of the earlier instruments. This probably would have been a 1960s instrument, and it used electromagnets. Okay, inside of this box there was an electromagnet. If you have physics or taken any physics, or you know that if you wrap a piece of metal with a wire and you apply a current to it, you make a magnet. Well, in the early days, electromagnets were what were used to place the sample inside of. And you could control the magnetic field, because if you applied more current, you got a stronger magnet. If you applied less current, you got a weaker magnetic field. And what would happen is the sample would go inside of the magnet, and then there was a pen, and what would happen is that you would vary the magnetic field and hold the radio frequency constant, so that when the sample absorbed the energy, you would see a peak, and the peak would actually just be drawn on a piece of paper. The pen would sweep across the page, and when it got to that point, you'd see a peak and then another peak, and you just basically sat there and took 10, 15, 20 minutes. It took longer than that to set the instrument up most of the time, because a lot of times it was broken. And this is the type of instrument that I would have had in 1984-ish, when I would have been a sophomore, junior in college. So this is what we had. And this is what John Carroll would have had up till 1989, I think. That what we have now is much more sophisticated. But basically that's the way the older instruments worked. We applied the radio frequency, and then we adjusted the magnetic field. Nowadays, we have systems that are a little more sophisticated. All systems have these basic parts. Magnet for the magnetic field. The sample sits inside of a little tube. There's 2 radio frequency coils. There's a detection coil, and there's an application coil. So they're at 90 degrees. One applies the radio frequency, and the other one detects it. And then there's all the rest of the computer or non-computer parts. Nowadays, we don't use magnets that are electromagnets. Now, some people still do for certain techniques. Dr. Miller has an ESR, if you've ever seen inside of her lab. An ESR is like NMR, except it studies free radicals. And her magnet is actually a very strong electromagnet. It weighs like a ton, literally. There's like 2,000 pounds in that very small space, because there's a lot of copper and things that go into making strong electromagnets. Nowadays, we have what are called superconducting magnets, and so this is the one that's in the instrument room. If you've ever walked in there, you see it. It's called an R2-D2 magnet because it looks like R2-D2 from the Star Wars. The first Star Wars that's now renumbered as 4 or something like that. I can't figure that out. But inside of it is the magnetic material, and the sample actually is lowered into the magnet. And then all the electronic stuff is to the left of that. And actually the magnet's about 16, 17 years old now, and the electronics are only about 2 years old. Actually, the electronics, it's almost state-of-the-art. If it had a new magnet, it would be almost brand new. But that magnet's going to last as long as it will last, hopefully. That's our system. Inside of what are called superconducting magnets, you have superconducting material. If you learn about that in physics, a superconducting material is a material that at low temperatures has no resistance. So when you put an electric current on it, it basically has no resistance. And so the more current you put into that, the stronger your field is. The superconducting magnet is bathed in liquid helium. because otherwise it's not superconducting anymore. And then around the liquid helium, there's some liquid nitrogen to keep the liquid helium from boiling off too rapidly. There's a series of what are called dewars. Those are evacuated thermoses, in essence, to keep the coldness in. So the superconducting material then lets us produce really strong magnets. And all MRIs are incredibly strong magnets. That's why they tell you to take off all your metal stuff before you go in there. You know, wallets, it would zap all the credit cards and access cards and everything else. And those are much stronger magnets because you're the sample. In these magnets, the sample's only 5 millimeters wide. So these magnets can be strong, but they're not as strong as MRI. So the material sits in here, and basically once the power is applied to it, it will not lose any of that power as long as the resistance stays 0. I have to fill our magnet every 3 months with liquid helium, and then every other week it gets filled with liquid nitrogen to keep the liquid helium from boiling off. If something bad was to happen to it, which is called a quench, then what would happen is that if the superconducting material ever reaches a temperature where it begins to resist, then the temperature goes up, it boils off the liquid helium, the temperature continues to go up, and eventually the whole thing just dies. And then they have to come in and fix it for like $10,000 or something like that. Although ours is at an age where nobody knows how much more life it has, because these things were made 20, 25 years ago, and so there's very few of them still out there because most people have already replaced them. And it could cost $150,000 if I have to buy a new magnet. So every time I fill the liquid helium up, it's an adventure. But this is sort of the inside of a bigger magnet. And then these things contain so much energy. When you think about having a liquefied gas and all of this electrical energy in there, if anything ever got out of hand, it would just basically like blow up. And I've never seen that happen, but I'm sure that's probably really bad. So what we do is we measure magnetic field strength, not in Tesla. In physics, you talk about magnetic fields in Tesla. Ours is a 7.2 Tesla magnet. But in NMR, we measure the magnetic strength by how much Larmor frequency it takes for the proton nuclei. So that little table thing I showed you was 60 megahertz. The proton nuclei were precessing at 60 megahertz. Ours is a 300 megahertz instrument. That means it's 5 times stronger. Down at Case, and I think Ohio State has one of these, they actually have a 900 megahertz instrument, which is 3 times more powerful than our magnet. Our magnet's pretty small. This thing has like its own room that it sits in. And that room is probably about the size of this wing of the building. It's huge. I mean, that cell phone picture doesn't necessarily do it justice. But in order to put the sample, usually we put the sample on top, and it gets lowered in. There's a stairway, and it has its own little walkway to walk on top of where the magnet is. And then down here, you could actually almost stand underneath it to do whatever you got to do underneath the magnet. It's huge. There's just humongous amounts of liquid nitrogen in it, liquid helium in it, energy in it. I mean, it's probably would be the equivalent energy-wise of a couple of megatons of whatever. It's pretty powerful, and the magnetic fields are very powerful as well. So this is from like a control room. There's no real computer systems in there. If they are, they're very far away. This magnet is also what's called shielded to somehow keep the magnetic fields from penetrating beyond the magnet itself, but all that metal is non-magnetic. The roof goes up like a triangle because magnetic fields, have those particular shapes. And so everything has to be contained in there. And there's 2 or 3 other smaller magnets that are in this room as well, but that's pretty impressive when you actually go down and see it. That's the first time I'd seen anything that large before. Why would you need something this large? Well, if you're going to look at a protein, there are thousands of protons, and in order to get good resolution and see each individual proton, you need the strongest magnetic field that you can get. And right now it's about 900 megahertz. I don't think there's anything commercially available over one gigahertz or whatever it would be called. That's about probably at least 10, that's about 10 million in terms of the instrument and all the stuff that goes with it. And that doesn't even include construction of the special building. I think Akron has the money to buy a 900 megahertz. They have an NMR center that's pretty phenomenal as well, but they don't have a place to put it. So you almost have to build a building around this thing. So that's probably in the order of about 10 million. Ours is like maybe 300,000 for 300 megahertz. It goes up exponentially as you go bigger and bigger. But this is actually in what's called the Center for Structural Biology. So this instrument's used to determine protein structure from people from Case, the clinic, from all over, literally probably all over the world. Okay. So the magnet technology has changed over time, and we have something that's pretty good, but not as good as this. Now, what's important is the idea that your precessional frequency then is dependent on the applied field. Okay, that's something to keep in mind. Now, what does NMR tell us about the structure of a molecule? Well, it turns out that if you have a sample, not all of the protons have exactly the same magnetic field or precessional frequency. Okay, they're affected by a number of things. If you think about a proton, what is a proton? It's the nucleus of a hydrogen atom. Well, what surrounds the hydrogen atom? If it's bonded to something, electrons that are involved in the chemical bond. And so that Larmor frequency turns out to be affected by the electron density that surrounds the nucleus. And even the smallest changes in electron density can be picked up by the instrument from the nucleus having a slightly different Larmor frequency. And the way to explain this is kind of like this. When you have electrons that surround a nucleus, the electron cloud kind of sits in between the nucleus and the applied field. The applied field is the big magnet. Okay? Now, electrons, when they're in a magnetic field, they spin and orient themselves so that their magnetic field is opposed to the applied field. In the ground state, the nucleus's field is aligned with the magnetic field, but the electrons align themselves opposite to the applied field. It's something having to do with that right-hand rule in physics, right, where you got the thumb thing, and I've been seeing that for about 20 years. But the key thing is, you can kind of think of this, that if you had three magnets and you wanted to stick them together, what would you do? Well, you'd have one magnet then oriented north to south, and those two would stick, and then you put a third one on there, and it would be oriented, in that same direction to the third one. So the middle one would have a different orientation than the two on the end. Then the three magnets would stick together. If they all were aligned exactly the same way, they'd repel. So the electrons then, in the ground state, orient themselves opposite to the field. That means that they, what we call, oppose the field. So if you're the nucleus, and you're trying to see what's being applied to you, the electrons are going to subtract from that. So what we have is what we call an effective field. The effective field is what the nucleus sees. And the nucleus sees a field that is applied minus whatever the electrons use in that, or have themselves. Okay, mathematically, for instance, let's say that I applied 10 10 units of magnetism. And the electrons produce a 2. But that 2 is negative, right? Because it's oriented in the opposite direction. What does the nucleus see? Does it see the full 10 that's being applied to it? No. The nucleus sees 8. Because 10 is being applied to it, but 2 is being subtracted from by the electrons. So it only sees 8. Okay. So what? Well, here's the point. For the nucleus to flip, for it to absorb the radio frequency energy, those magnetic fields have to be the same. In other words, what I apply has to match up with what the nucleus is. So in this case, let's say the nucleus really has a field of 10. That's its magnetic field. How can I make the nucleus flip? Apply 10 to it. That brings it into what's called resonance. When the magnetic field of the nucleus and the magnetic field that's applied to it are equal, the magnet or the nucleus absorbs the radio frequency energy and it flips. Okay, this is using the older kind of way that we do the experiment. So in other words, what's applied to it has to equal what the nucleus is. Well, if I know the nucleus is 10 magnetic units and I apply a 10, it's not going to come into resonance, right? Because the electrons are going to take some of that 10 away. So what do I have to do? If I want to bring this nucleus into resonance, what do I have to apply to it? 2 more. I got to apply 12. So if I was to apply 12, then the 12 would have 2 subtracted to it, and all of a sudden, instead of 8, I would now see 10. The nucleus would now see the magnetic fields would match. It would absorb the radio frequency energy, and now it would flip. So whenever a nucleus is surrounded by electrons, I always have to apply a higher magnetic field to overcome the electron's opposite field. That's the bottom line. Okay? The electrons oppose the applied field, and so I have to apply a greater field to overcome the field of the electrons. Okay. All right, does that make sense? Well, basically we call this, what the electrons do, shielding. When the electrons apply a field that's opposed to the applied field, the electrons are said to shield the nucleus. And that kind of makes sense. They're shielding the nucleus from the full magnetic field. So the more electrons there are, the more shielding goes on. And the more shielding that goes on, the more magnetic field I have to apply to overcome that shielding. Now, let's draw out a little field, or a little spectrum. Okay. It turns out that with this spectrum, the right side has that's where the high field end of the spectrum is, and on the left-hand side, that's where the low field is plotted. Okay. So the magnetic field on an NMR spectrum increases from left to right. Okay, higher fields to the right, lower fields to the left. Now, in terms of the Larmor frequency, and there is unfortunately no direct relationship without getting into a rotating frame of reference, which I'm not going to do in this class. We barely survived that last semester in the advanced spectroscopy class. But without getting into that, it's an inverse relationship between Larmor frequency and field. In other words, the faster the nucleus spins, the smaller its little magnetic field that it has, and vice versa. So in this spectrum then, the high radio frequency end is on the left and the low radio frequency end is on the right. So these are inversely related, and you'll just have to accept that without getting into all the brutal details. Okay. All right. So if this is the direction, if this is the way the NMR spectrum is recorded, which direction does shielding go in then? If shielding means that I have more electrons and I have a higher field that opposes the applied field, and I have to then apply a higher field to compensate for that, shielding goes in this direction. Okay, so a peak that's on the far right-hand side of a spectrum, that proton is more shielded than peaks that are on the left-hand side. Okay, so as you go from left to right, that's where the protons become more shielded. Okay, so they have greater electron density around them. Okay, kind of makes sense? Then if you take away electron density from outside of the nucleus, that is called deshielding. And deshielding then goes in the opposite direction. So if you go from right to left, that turns out to be the direction that we call deshielding.
So it's taking more electrons.
So shielding means that I have more electron density, and this is more electron density around the proton nucleus, and deshielding means that I have less electron density around it. And I'll show you a concrete example of that in a minute. So shielding means more electron density around the proton. Deshielding means less electron density. Now, I'll just tell you ahead of time, next week we're going to have a quiz, because I promised one to Tuesday, and there are no pop quizzes in a lab, because unless you have no friends, you would know that Tuesday got a quiz. And so I promised them a quiz, and that means everybody else gets promised a quiz. And the quiz will be to, if I give you an empty spectrum, tell me what the low field, the high field, the low frequency, and the high frequency ends are, along with the directions of shielding and deshielding. Yeah, I know, it's like, why bother? Well, because we need some quiz points, and, you know, hopefully at least for the 5 minutes that you're taking the quiz, it'll be in your head. So that's part of the quiz for next week. Okay, so that's the direction that we're going in. How do you shield or deshield a proton nucleus? Well, unless you've got a totally naked proton floating around, it's going to have electrons around it. I mean, I suppose if you had a proton totally in the gas phase with nothing but vacuum around it, it would be perfect, but that's never the case. So in terms of the shielding and deshielding, what we need to do is we need to look at this in terms of what's attached to the hydrogen. Well, what is attached to the hydrogen? 9 times out of 10, it's a carbon atom. So the electrons that surround the nucleus are from the carbon-hydrogen bond. Well, here's how I can de-shield. I'm going to de-shield first. Let's say I attach a halogen, like a chlorine, to my carbon. You may say, Wait, I thought you were talking about changing the electron density around the hydrogen. Yes. How does adding a chlorine to the carbon do that? Well, it does. What happens to the carbon-chlorine bond? It's polar covalent, correct? Correct. The chlorine becomes slightly negative, the carbon becomes slightly positive. The chlorine's doing what? It's sucking the electron density out of the carbon. How's that affecting the hydrogen? That's the electrons that are surrounding the hydrogens are the ones from the carbon. So if I take electron density out of the carbon, I am in essence taking it away from the hydrogen nucleus, which is the proton, as well. So that means that what have I done here? That means that I've removed some electron density. In essence, I've done what to the proton? I've de-shielded it. And which way will that, where will I find that peak on the NMR spectrum? To the left or to the right? Well, the de-shielded region is going to the left, so that peak will show up on the left-hand side of the spectrum. So when we talk about shielding and de-shielding, we're talking about affecting the proton's the density around the proton, but by attaching different things to carbon. How do I shield? Well, the best way to shield is to add an atom to the carbon that is less electronegative than carbon. And these shielding and de-shielding terms are relative. Okay. But here's a molecule that's called tetramethylsilane. We'll talk about it more next week. Tetramethylsilane is also abbreviated TMS. In this case, what have I done? Well, in this case, I've attached a silicon atom to a carbon. Silicon is less electronegative than carbon, which means that now the opposite happens. The carbon becomes slightly negative, and the silicon becomes slightly positive. So now it's the carbon that's sucking the electron density out of the silicon. So what happens to the amount of electron density around the hydrogen? It now increases. So now my electron density is increasing around the hydrogen. Why? Because it increased around the carbon. Why? Because the carbon sucked the electron density out of the silicon. That leads to that proton being shielded. So this is a situation where shielding occurs. Does that make sense to everybody? Michelle?
When you're trying to de-shield or shield, can you only add things? You can't remove anything from the molecule? Like when you're shielding, can you get rid of like chlorine?
Well, when we talk about shielding and de-shielding, first we have our molecule that's set. I don't try and shield and de-shield. I explain where the peak occurs, whether it's to the left or right-hand side, by shielding. But the extreme would be just having a naked proton with nothing around it. That would be the most de-shielded. And that just doesn't happen. So what we're going to do is we'll look at a series of peaks, and what we say is, well, this peak is more shielded than the other. That must mean that the hydrogen gets attached to a carbon with an electron withdrawing group, with a more electronegative element. And we'll see in coming weeks that what happens is if you attach a chlorine to a carbon atom, the hydrogens that are directly attached to that carbon are the most deshielded, but then the carbon next to that is a little bit deshielded, and the one farther away is a little bit less. So you actually see different peaks occur at different points because they're farther away from the chlorine atom. So the effect is really subtle, but it's also measurable. Okay. So this is the second half of the quiz. The first half of the quiz is just to fill out the chart. Tell me low field, high field, high, low radio frequency ends, directions of shielding, deshielding. The second part of the quiz will be if I gave you this molecule and said, explain to me why the hydrogen is deshielded, you could draw that diagram and say, the chlorine's removing electron density from the carbon, that removes the electron density from around the hydrogen, it deshielded it. If I gave you this molecule and said, tell me why this one is shielded, opposite argument. Okay. So that's, in essence, how we get the shielding and deshielding to occur in the molecule. It's not what's attached to the hydrogen, because what's attached to the hydrogen is a carbon. It's what's attached to the carbon that's attached to the hydrogen that affects the hydrogen's electron density. Everybody's still kind of with me? We're almost done for this week. This whole page just talks about shielding and deshielding from how I have to apply the magnetic field. It's higher or lower to get it to what it's shielding or deshielding. If it makes sense to you, great. If it doesn't, just remember the way that the fields are oriented on the chart. All right, so let's look at some real spectra here. And again, peak positions from our spectrum, we know that shielding is to go right to left, or deshielding goes right to left, shielding goes left to right. Okay. I literally have gone an entire lecture with those two backwards. Unfortunately, that was a lecture where I was being observed by a senior member. Like with 5 minutes left, somebody said, don't you have this backwards? And I go, yeah, I had it all backwards. Then I said, I'm illustrating that you have to be careful and you have to try and figure this out in your own mind. So you really kind of have to think of the directions. It's really easy to get these. In NMR, there's 15 different inverse relationships, from Larmor frequency to applied field to shielding and deshielding and high field and low radio frequency. But I haven't gotten it wrong yet, not today. So here is where the TMS peak would show up. Next week we're going to learn that TMS is actually our reference compound. And we call the peak that occurs there, that's our zero on the x-axis. We'll talk about what the x-axis means next week. But here are 3 or 4 molecules with chlorines attached to them. So here's where the peak shows up if it's just methane with 4 hydrogens. Okay, that peak is more shielded or more deshielded than TMS, but it's on the right-hand side, so it's essentially a shielded system. But notice what happens when I add the first chlorine. When I add the first chlorine, the peak moves to the left. That's in the direction of deshielding. I add a second chlorine. Those hydrogens are even more deshielded. I add a third chlorine. They're even more deshielded. Why? Because every chlorine that I add here is removing electron density from that carbon and therefore from the hydrogens. So the more and more chlorines I add, the more and more deshielded the protons become. Now you could say, why did you put 4 chlorines on there? If I put 4 chlorines on there, there's no proton nucleus to see. So that's as far as we can go. But each one of those is the real peak position, and so you can see the more shielded it gets, the more the peak moves to the left. So what we're going to end up doing is looking at proton spectra that are going to have peaks on different positions on the x-axis. Well, that's going to tell us about their shielding and deshielding, but more importantly, it's going to tell us about what's attached to that carbon that the hydrogens are attached to, and it's going to help us figure out the structure. Okay? But the shielding and deshielding comes about because of what's attached to carbon that affects the hydrogens. And these are really, really subtle effects that we can see. Okay. All right, so that's where we'll stop today. So next week, the quiz will be over what I've told you. You'll get a chart with 6 things that you'll have to fill in: high field, low field, high radio frequency, low radio frequency, shielding and deshielding. And then I will ask you to do show me how shielding and deshielding works in 2 molecules.